Hi, my name is Seth Kinoshita, and this is Lab 3 for Physics 2211, Black Hole. In this session, I will first go through the introduction and the physical principles. Then I will describe the initial conditions, the systems, and the surroundings. Afterwards, I will go a little bit into the computational models and the results that came from them. Finally, I'll answer the what if and the what does this lab mean questions. So the purpose of this lab is to computationally determine the mass of a black hole, and with this value, determine the initial velocity required for a spaceship to not crash into this black hole. However, to do this lab, I first had to have a good grasp on parallel and perpendicular forces as related to circular motion. After all, we are finding the mass of a star in orbit around the black hole and the velocity required for circular motion, so understanding these two components is key. So the left diagram over here shows uniform circular motion, and the forces acting on an object moving in this trajectory. While orbits in space are usually ellipses, the same concept is still applicable. As seen, the perpendicular vector always points inwards relative to the object's position, and the parallel component is tangent to the path at the object's current position, seen here, and points in the direction of motion. A derivation for the formula for the perpendicular component is shown on the right, where the change in momentum over a change in time can lead to this formula that expresses the net perpendicular force in the direction of the inward unit vector n hat, and this formula is mv squared over r. Another important concept to understand when dealing with planetary bodies is the force of gravitation, seen with this formula here, where the force of gravitation is equal to g times the mass of the first body times the mass of the second body over the distance between them squared. So it is defined as the interaction of two bodies on each other due to the force of gravity, and is usually applicable to planetary bodies because of their large mass. And this really does matter for black holes because they often have a mass so large that the force of gravity on anything around it is gigantic. And this means that to escape a black hole, a large initial velocity is likely required. So the initial conditions for part 1 of the lab include the gravitation constant g, where it's 6.7 times 10 to the negative 11th, the mass of the star, which is given, and the delta t, which is the time step. So 86,400 was chosen because it's the number of seconds in one day, and to make a complete orbit, we wanted 365 data points. Therefore, the clock should be advanced one day at a time to get the proper number of data points. The initial conditions for part 2 of the lab include g, the planet and ship mass, the time step delta t, the max simulation time, of which I used the default of 1 hour, and the mass of the black hole calculated in part 1. So delta t is only 1 second here because we are not looking for a full orbit, but rather if the spaceship can avoid the black hole. So a little preview of the results is that the mass of the black hole shown here actually had to be averaged because there were multiple values over many time steps. Additionally, the initial velocities had to be found through a guess and check method rather through an actual calculation. So, in part 1, the system was defined as the black hole and the surroundings were defined as the star, and in part 2, the system was defined as the spaceship and the surroundings were the black hole and the planet. So for the computational model in part 1, so the momentum principle was applied up here in P initial and P final to calculate the initial and final momentum, and then the relationship dp dt, which was described earlier, was used to calculate the net force acting on a black hole, and to define what the parallel and perpendicular components of motion are, shown here. And then we use a rearrangement of the gravitation formula shown earlier to find the mass of the black hole, which is seen here, and it uses quantities calculated in earlier steps of this computational model. And the results are shown here for a full orbit, and the magnitude of the net force was determined to be about 9 times 10 to the 28th, and the magnitude of the parallel force was about 2.3 times 10 to the 28th, and of the perpendicular component of the net force was about 8.7 times 10 to the 28th. The average mass was determined by averaging the mass of the black hole across all time steps, which was about 1.39 times 10 to the 34th. And then this is the computational model for part 2. It looks like a lot of text, but all this text up here is just the gravitation calculation for the net forces on both the planet and the ship. So the other two objects for each of the planet and the ship had to be taken into account for the correct formula. And then using these net forces, the planet and ship positions could be determined at each time step to ensure that they did not crash into each other. And so this is also the position update for the planet and the ship right here. This is was used in both labs 1 and 2, so it is a continuation of the concept. And after an hour, the simulation resulted in this flight path, and the initial velocity was negative 1.2 times 10 to the 7th in the x direction, 1.02 times 10 to the 7th in the y direction, and 0 meters per second in the z direction. And this initial velocity was quite large, but it was sufficient enough for this ship in purple to kind of go around the star and escape its gravitational pull. And as seen here, a distance of 3.7 times 10 to the 10th meters away is sufficiently far away enough from an event horizon. So being able to run the models is important, but it's also key to apply these concepts. For example, the parallel and perpendicular components were discussed heavily in this lab, but how are the parallel and perpendicular components of net force different than the same components of the rate of change of momentum? So the perpendicular component of net force is mv squared over r times n hat, and the f parallel is d times the magnitude of p over d hat over dt times p hat, and this requires you to find all the forces acting on the system. However, the rate of change of momentum is equal to dp over dt, where p is the mass times velocity, and the parallel is just magnitude, and perpendicular is the change in direction. And this is just the change in momentum when it only requires you to find the change in velocity of a system versus all the forces acting on it, like in the perpendicular and parallel components of net force versus that of momentum. And so what initial velocity would be required for the spaceship to enter orbit? So a similar velocity, but slightly different components to avoid crashing into each other. And so the initial velocity that I found was negative 2.4 times 10 to the 6th, 1.02 times 10 to the 7th of 0 meters per second. Increasing the time would show a complete orbit, but as you can see, the ship in magenta does travel in an orbit-like pattern around the center, and it almost matches the orbit of the star without crashing into each other. Thank you.